Okay, what about this situation where we have more variables than equations? So let's do an example. Just a fairly simple example of this would be something like the following. I'm going to try to use the subscripts. So x1 plus 3x2 plus 5x3 is minus 7, and 2x1 minus 3x2 plus x3 equals 4. Okay, so that's two equations, three variables. And if you think of each equation as a constraint, like these are both planes in 3D space, and we're really intersecting them. And if you intersect two planes in 3D space, you might be able to guess what's going to happen here geometrically. But let's convert to augmented matrices, again, because laziness mainly. It's just faster to write. And then do row reduction steps. And really, you might, well, there's a couple steps here because the first one, well, I'll tell you the first one, and then I'll just sort of, again, I'm going to ask you to fill them in. The first one, you could take the second row and you could subtract twice the first row, right? And that would clear out this 2 and make it a 0. So if we do that, check my arithmetic, but I got the following: minus 9, and 18. So subtracting twice the first row from the second, okay? And then, well, you can probably guess what this is. I'll put a question mark, you can put it in yourself. If I can simplify the second row, right, to look like that. I could stop here, but I want to do one more step just to, oh, this is a minus 2, is that, sorry. Yes, and then the one more step I want to, I'm actually going to clear out, again, just to make things look a little nicer, I'm going to clear out that 3. Use a second row to clear out that 3 and make it a 0. So again, ask yourself how you would do that. And then I get the following. Something like that, okay? And now it's good to translate this back into equations. So the equations become x1 plus 2x3 equals -1, and x2 plus x3 equals -2. And what this means, if you remember from the chemical equation example, is we have this one column that we're calling a free variable column. And the idea is that, right, x3 can be anything we want. X3 is free, but then that forces x1 and x2 once you pick a value of x3. So one way we can write this is we can say x1 equals -2 x3 minus 1. x2 is -x3 minus 2, and x3 is just x3 free. So you could find solutions. So in fact, this has infinitely many solutions. And you could find solutions all you want. You could say, let's even just say x3 is 0 for a very simple solution. That would imply that x1 is -1 and x2 is -2, right? And you can check that if you, well, so that gives the solution -1, -2 is 0. And you can check that if you take this and plug it all the way back in to here, that actually does work. That gives you the correct, those do fit the equations. But we could also let x3 be 7, or x3 be 42, or x3 be -pi, and that would also give us solutions. So this gives us infinitely many solutions. And again, underdetermined, you might think, okay, so this two planes are intersecting actually in space. If we had two planes intersect, they intersect in a line. And so that was that is why there would be infinitely many solutions. Does this mean we always have to have infinitely many solutions? Well, no. In fact, I'm going to construct an example. I'm going to tell you how I construct it too, to show you that this doesn't have to have, we don't have to have infinitely many solutions. So here's a basic example. What if I'm going to actually do 3 equations in 4 variables? So again, fewer equations and more variables and equations. Okay, and I'm just going to come up with the most basic thing I can. Here's an equation in 4 variables. Here's another one. What would I do? X1 plus 2x2 plus 3x3 plus 4x4 equals 5. And I'm going to make the third equation by adding the first 2 equations together. But actually, instead of adding the 5 and the 1 and getting 6, I'm going to just change this to be a different number. Like, let's say it's 8. Okay. And, well, what's going to happen? I claim it's going to screw something up. It was the sum. If the third equation was the sum of the first 2, that'd be nice, because the third equation would in some sense be redundant. But if it's not, well, what happens? You should row reduce this yourself. But it's only a couple steps. When I do it, okay, so clearly the first step is going to subtract. I'm going to do row 2 minus row 1, and then, yikes. Let me see if I can write this. Row 2 is row 2 minus row 1, and then row 3 is row 3 minus twice of row 1, right? Because we're going to clear out this 1 and this 2 right here. Okay, so if we do that, again, pause frequently, check the arithmetic here. Get this, and then I actually get, so now you start to see, actually, if you do this, I think you get the following. So notice the second and third row now look very similar, except the 6 and the 4. And so if we do the next step of subtracting the, if we're gonna, let's say, clear out, try to make this a 0 right here, if we subtract the second row from the third row, make that the new third row, then I guess this is, sorry, R3 becomes R3 minus R2. Okay, this second row doesn't change, but the third row, we get 0, 0, 0 straight, and then we get 6 minus 4, which is 2. And then again, now we have 0 equals 2. And that is bad. And this has no solutions. So I contrived it exactly to have no solutions. Okay. Final question for you to think about. Is it possible for an underdetermined system to have a unique solution? That's my question for you. Could you come up with an example where you end up with just exactly one solution, like x1 equals something, x2 equals something, x3 equals something, x4 equals something? And the question then is why or why not? Okay, I'll stop there.